Welcome back, everyone. I'm Akash Joshi. I'm the Operations Research Guru, and today we're going to be talking about linear independence and dependence. So, linear independence and dependence is important to understand once we get into the algorithms of linear programs. Okay, let's get into it. So let's first talk about linear dependence. Okay, so say that we have the vectors x1, x2, and so on until xy. So we have y vectors. The vectors are linearly dependent if a non-zero vector w exists where w1 times x1 plus w2 times x2 plus all of them up to wy times xy equals 0. So basically we have a vector w and we're multiplying it by each of the vectors, taking their sums, and eventually once we add all of them up, we'll get 0. So if we know y minus 1 vectors out of the set y, we know the missing vectors since the y minus 1 vectors added to the last vector would equal 0, and then we would just solve for that final vector. So if all the vectors added up multiplied by a non-zero vector, if they all added up to 0, then they are linearly dependent. Another way to think about this would be if we have a matrix that represented a system of vectors, and then if we performed Gaussian elimination. I made a video on Gaussian elimination, so please check that out if you don't know what I'm talking about. Otherwise, don't worry about it. Okay, so after we perform Gaussian elimination and the final row is all zeros after elimination, that would suggest that this is linearly dependent because 0 times w1 plus 0 times w2 plus 0 times however many vectors there are would equal 0, suggesting that the system of vectors is linearly dependent. So if the number of pivots in the Gaussian elimination, if the number of pivots in that process is less than y, which is your number of vectors, then you know that they are linearly dependent. Okay, let's get into linear independence now. So we have the vectors, and we know the vectors are linearly dependent if w1 times x1 plus w2 times x2 plus blah 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 is equal to 0. However, they are linearly independent if this does not equal 0, and if y is greater than n, with n being the number of dimensions of the vectors. If y is greater than n, then they are linearly dependent. The vectors are linearly independent. Okay, so if we know y minus 1 vectors, we wouldn't know the missing vectors since they don't add to 0 because they are linearly independent. And this is really important. This comes up a lot in linear programs. Keep that in mind. Remember, if y is greater than the number of dimensions of your vectors, then the vectors are linearly independent. Okay, another way to think about this would be if we have a matrix representing a system of vectors like before, and then if we perform Gaussian elimination and the final row wouldn't be all zeros, this would suggest linear independence because 0 times w1 plus 0 times w2 plus blah 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 does not equal 0. And yes, these are the coefficients that are expressed in the final row of the matrix. So if the final number, the final column, final row of that, the term in the final row, final column of that matrix, if that's not 0, then you know that it doesn't add up to 0. And therefore you know that this system of vectors is linearly independent. Another way to think about that is if the number of pivots in your system of vectors, once you perform the Gaussian elimination, if that number is equivalent to y, which is your number of vectors, then you know that your system of vectors is linearly independent. All right, that's it for today. Thank you for watching. See you next time. Goodbye.